Well, then I'll start by saying thank you all for coming. You have no idea how happy we are that you're here. And ta-da! And to start with something fun. Yeah. Like this? Okay. Oh, no, but then I have to stand behind. No? Okay. Okay. I'm going to stand behind the computer. With HBM provided us with a cool tool where we can ask questions, and you can ask us questions if you're too shy to get up. But by all means, just raise a hand and talk to me, because the room is so small I can hear you anyway. It's all right. But if you go to this website and then look for our session, which is 6 or 7 in the line, I think, then you find that there's questions to ask, and you can respond to polls as and when they appear. I opened one. Just so there will be something for you to answer. And I'll give you 10 seconds to get through and click on stuff.
But of course, since this is a relatively small room, just feel free to ask questions in the way that the Romans did it many years ago.
Which is how? Okay. So, the more serious part. So why do we talk about spins in physics when it's a session on laminar function and how to study that? Well, basically, because to study anything like a column or a layer in the human brain, we need very, very high spatial resolution, and that means we have very high requirements on SNR, on spatial resolution, but also on the sort of bold responses that we'd like to observe. So I divided my talk into these 3 topics. And the first will be the SNR. So how do we get SNR? How do we get a signal at all in MRI? Well, we all know, I hope, that protons have a property called spin, which means that they behave a little bit like a magnet. And in a magnetic field, they are semi-aligned with that magnetic field. They spin around the main magnetic field, either just off-kilter parallel to it or anti-parallel. And the division between these 2 states, aligned and anti-aligned, is given by the energy difference between these 2 states. And what you have as a net magnetization factor, the signal that you're going to work with, is the difference between the aligned ones, and so the spin ups and spin downs. And the distribution between these 2 states is given by the Boltzmann distribution. So it's a pretty simple enough equation, and there are a couple of factors in there which are interesting. So the first would be the temperature, and in the energy difference, we have the magnetic field strength and the gyromagnetic ratio. So the gyromagnetic ratio is dependent on the type of atom that you're observing. We're pretty much stuck with protons, so that's not really something we can choose, but B0 we can change, and the temperature we could also change, at least in theory. So if we start with a field strength of 1 Tesla, just because that's a nice round number, and room temperature, then we have a difference between the spin ups and spin downs of only 6 in a million. So a million spins up, down, and 1,000,006 up. So that's a very, very small difference. So the signal that we're working with is also incredibly noisy. Right? This is inherent to MRI. It's for every single MR experiment. We're sort of stuck with this tiny little wiggly signal and having to measure for a long time. The good thing of this is that we can change it. So if we have 6 more spins up and down at 1 Tesla, there's 42 already when we go to 7T. And that brings us to the happy situation where we can manipulate how much signal we have. So if we move from 1.5 to 3 to 7T, then we see a nice upwards going curve, slightly depending on how you do your experiment. Can I see my mouse? Yeah. So we have a very steepish line. If you eyeball it here, it already looks a little bit more than linear. And certainly in the Pohmann paper, which is probably a classic figure on how SNR behaves at high field, we have a really superlinear increase for SNR with field strength. Luckily, for those of us that really want to do laminar imaging, in the cortex it even seems to be a bit better than that. And that means that if we take the same brain and the same images and we acquire them at higher field, then we can see, even just by looking at them, that we have a higher SNR in those images. What you can also see from these, and the projector is actually good enough to show that, is that the contrast changes a little bit, and the overall aspect, so the amount of bright and darks in the images changes also. So we don't just have an SNR increase, there are other things to deal with also. But there's this other factor that we could change, and I felt I really had to put a slide in out here. So if we look at our equation spin up, spin down, and then the easiest way of getting it to 1 is by bringing the temperature to 0 Kelvin. Now that might be very unpractical if you're scanning humans, let's say. They might not like to be frozen to that point. But what you could do is bring something to a very, very low temperature indeed, polarize it, and have polarizations of up to maybe 60% or so. And then quickly infuse it into the thing that you're actually trying to study. Warm it up first, then infuse. And if you choose that clever, you can, say, have a precursor to some metabolic event, inject it, and then see how it gets distributed further on in the body. Now, that might look risky, but it's something that's actually being done in humans, in this case, to study tumors and how their metabolism works. Again, I don't think that this is hyperpolarization is quite ready for applications in laminar fMRI, but I thought I'd show you this slide regardless. Perhaps you can think of a way of making it useful. What is practical and a lot safer is getting the very best receiving of the signal that you have. So you've got a strong magnet, and now you would like to take as much out of it as you can, and you do that by getting the very best RF coil. And that this is a popular approach. You can see by just looking at the publications in PubMed, there's a very steep increase, which started already in the 80s. People try and really make the most out of this receive coils. So, and why is that, and what can we choose there? Well, generally, large coils provide large coverage. So this is a diagram from a 3T where you have a massive body coil and then very large ones on the body. But you can change that coverage in a smaller coil for signal. So if we have a smaller coil, then closer to that coil, you have a lot more signal. So the distance here, no. So that if you look on the x-axis here, it's a distance from the coil. And if you're close enough to, say, 2 centimeters or 3, which is luckily the case for a lot of the cortex, then you can gain loads of signal there. So I have an example coil here, which is really targeted specifically on the visual system. It'll only image the back of the head. It'll only image, let's say, superficial 2 centimeters of that back of the head, but it will do so with incredibly high SNR. Something else to take into account is the fact that the transmit B1 is not homogeneous, which is a disadvantage, and that it's something that we just have to deal with. When we move from 3T to 7T, the resonance frequency goes up, and that means that the wavelength in a human brain goes down to maybe about 11 centimeters, and those 11 centimeters compared to a human brain, which we also can't change the size of that, right, is too short. So we see the pattern in the B1 imposed on our brain signal. So the background here is a B1 map, and that it's a pretty dramatic image, but it's a factor 2 higher in the center than it is on the sides. And because we have a spatially varying B1 field, we get spatially varying flip angles. And of course, our sequences typically deal with the assumption that if you apply a 90-degree angle, that you get the 90-degree angle, which really you don't. It might vary anywhere between 130 and 45. What you can do, though, is use dielectric materials, which is a very cost-efficient way of dealing with this problem. So basically putting in this case, two pads of dielectric material on the sides of the brain to sort of pull the B1 further out to the sides. And this is actually a slide that I borrowed from someone that borrowed it from Leiden, so if the actual author's here, I don't think so, then thanks. But it's a very nice diagram of how dielectric pads work. You create an extra current that increases the local RF field just where you've placed the pad. So it's intuitive, and that you just put it there, and that's where you get more signal. And then it works, and this is an illustration of my own where I was looking at cerebellum, and then you see that there's, in the anatomical images, more contrast at the place where you put the pad in the neck, and that there's also more of a bolt response just there. Now, a better way of doing this, or at least a more flexible way of doing this, is by having a different type of RF coil, a multi-transmit coil, where you can better control the transmit field. So this is an example of an 8-channel one. And if we take care and make an effort of properly aligning these, the RF pulses from these coils with each other, then we see that there is actually a much more homogeneous field and contrast throughout the brain, right? And that also this is reflected in how much of a bolt response you then see in the area that you're interested in. So just to show it a bit larger here, we have this nice dramatic black hole in the back of the head. If we use our parallel transmit system, that becomes much more homogeneous. And what works for anatomy also works for function. So now we have lots of signal in a good space. We still need to trade that for high spatial resolution. And when we talk about high spatial resolution or about spatial resolution tool in MR, we always have to talk about K-space. And that might be a bit of a vague concept because we like to look at images, human brain maps, for example. But really what we acquire are not images. What we acquire are the spatial frequencies of the object that's being sampled. And we collect these in K-space. So K-space is not very nice to look at. Again, it's just a bright dot in the middle usually. But that K-space is actually contains the exact same information as our image space. So if we look at K-space, it's a Fourier representation of the object space. So we can apply a Fourier transform, very straightforward, to move between these two back and forth. Now, to give you a little bit more of a grasp on how that looks, acquiring spatial frequencies and then forming a comprehensible image with it, I took a Shep-Logan phantom here and then a line through that, and this doesn't look very much like a collection of sinusoidal waves, perhaps, but if we take one with an infinitely long one, then that would give us the average signal intensity, which is not a very good descriptor of the image. But if we start adding sinusoids to it, then this starts already to look a little bit like the object that we're interested in. And the more we add, the better we start to describe the phantom. So even though it looks like it couldn't be a collection of signs, it really is. And of course, that works in 1D. The same goes for 2D. So this is a slide I borrowed from a colleague where it says, well, if K-space is a Fourier representation of the object space, and it's called K-space incidentally because of the wave number K, or the number of cycles per unit distance. So they are pointing K-space at -3 would be 3 sinusoidal waves in both directions, right? So with that mask here. So that's a filter, if you wish, that we project our image onto, right? Or a measure at that point in K-space is how much of that particular sine wave is actually at that point. Its neighbor, or a few further out, would be a sine wave with a much higher frequency in the x direction and the same in the y direction. If you see the orange dots appearing just there, right? And it's symmetrical, so simply inversing the amplitude moves to the opposite side in K-space. We can, of course, move further down as well. Then we have a higher frequency in the y direction as well as in the x. And then we can mirror that to the top. And if we look at this collection, then it becomes more obvious that the furthest point in K-space, so the highest spatial frequency that we look at, is what dictates the spatial resolution of our image. Right? So there's no way of getting around this. If we want to have a very high spatial resolution image, we need to go very far in K-space. The opposite is also true. The distance between these points, the points that we sample, dictates our field of view. Okay, and this is a bit, it might be a bit tricky to sort of get an intuitive feel for, but once you start imaging more, putting more protocols together, this is something that helps to get a hang of what happens when you change which protocol. So how do we then sample points in K-space? What do we actually do? Well, we apply a current through an electromagnetic, an electromagnet with a linear varying field The simplest ones are actually the Z gradients, because it's just a loop, a wound loop. For the X and the Y patterns to fit around a body, you have to make a slightly more complicated design. And one of these electromagnets is shown here. So this is an actual Siemens gradient before it's put in the bore of a scanner. So it's no more than that. It's a bunch of copper wires on a tunnel. So when we switch our gradients on, I realize now that this is a 3T resonance frequency, but it doesn't matter. When we switch them on, then we create a magnetic field where the omega, in addition to our static magnetic field, where the resonance frequency changes with position. And if we have a change in frequency across the object, then we're imposing that sine wave that we had earlier. So this switching the gradients on equals a move in k-space. So if we want to go very far out in k-space, then we need very strong or very fast or both gradients. Right. So, ta-da, then it's time for my second question. So if you think about spatial resolution and the thickness of the cortex, then you should also be able to answer the question, what is the best spatial resolution for laminar fMRI? Now, I don't know how many of you filled in the first of the polls, but especially for the ones that do, what is your favorite spatial resolution? And for the ones that came in later, if you go to that website and then choose our session, you can answer the polls. You can also answer questions there, or ask questions for us to answer later. Okay. So, I already said we need a way of efficiently traversing k-space by using our gradients. David's going to talk a little bit more about sampling strategies, but the basic choice is between either doing that line by line and a gradient echo type thing where you move out to the edge of k-space, acquire the line that you want, and so on and so forth. This is quite a slow and tedious process. It's high SNR, so it is sometimes used, but typically for fMRI, people give the preference to echoplanar imaging because it's really fast. You can tell, though, by looking at the sequence diagram, that this is already a very long echo train. Now, if we're thinking of how do I get as far out in k-space as I can, then these echo trains quickly become prohibitively long, or your gradient simply can't do it anymore. So there's a bit of a limitation there in how good your system is, how much you would really want to achieve. What helps, though, what really helps, especially if we're looking at sub-millimeter resolutions, is parallel imaging. So, in case you are not familiar with this, I made the one-slide summary. If we have an image with a limited field of view, then, like I said, we're acquiring points which are too far apart in k-space to properly sample all of our image. And we see that the second half folds back onto the first half. But if we now acquire that image with two coils, one of which, coil 1, acquires signal mainly from the nose, from the left side in here, coil 2 is mainly on the right, then both of these will acquire an image from the same brain, but they will look very different because it's so heavily weighted towards where these coils are. Now, we can know where the coils are because we know where we put them. We can also measure where their sensitive areas are. And if we combine the image that we acquired with the information that we get from the coils, then we can unfold both of them and combine them to become a joint normal image. So what we're doing here is taking two large steps in k-space to be able to get to where we want to be in terms of resolution. And then we use coil information to fill in the blanks. Yeah? And the way that helps is by shortening the readout. Of course, it does mean that you need a good RF coil that can actually help you fill in those blanks. Okay. So if you do that, if you drive that to the extreme, then you can acquire extremely high resolution data. This is a 0.35 millimeter anatomical scan, which is probably a little bit too high for defining lamina on, but it's very good at showing other nice anatomical details like the striatum area here. And this is an example of a 0.7 millimeter 3D EPI, which is our standard laminar protocol. The image on the right scrolls through the slices. The image on the left is actually a movie in time. You have to kind of look at it to see that it's actually moving, but it is moving. The subject is staying pretty still. There's a little blip at the end. So what we see here is that I've pushed it quite far in terms of SNR. These are grainy images, but there's many, and that still gives us enough information. So then we have a lot of SNR. We've used it to get high resolution images. And now what are we actually looking at? Well, we're studying the Bolt signal, which is, I probably don't need to explain this to anybody here, but is a very complicated thing. There's a stimulus that introduces or enforces some sort of neural activation. And through a coupling to the vascular system, we then have a change in the blood oxygenation level, and that we detect with the scanner. So the two relevant things, or the only things that you should extra consider if you're going from a standard resolution to something laminar, is the magnetic field strength and the echo time, and possibly whether or not you want a spin echo or gradient echo readout, but that's not part of this talk. So in terms of field strength, this is a nice summary graph of a single subject doing a motor task, and 2 hands just finger tapping in the scanner 3 times. One's at 1.5T, one's at 3T, one's at 7T. And now, would you see that on top of the SNR increase that you already have for 7T, you have a massive increase in the Bolt response. So, of course, measuring a motor response is not very difficult. So we have a solid response even for the 1.5T, but the increase is it's more than double, right? So, and that's again maybe not so bad if you're doing if you're studying the motor system, but if you're trying to look at more subtle things, then the difference in power that you get from a 7T can really be like the difference between running your experiment or not running it at all. This is an image from a colleague of mine that works on numerosity mapping. So she looks at how many dots are there on the screen, 2, 4, 6. And then she creates these beautiful rainbow maps on the parietal core surface. And to do that, they have a model which measures how high the explained variance is. And then if you compare how long you have to measure at 3T versus how long you have to measure at 7T, then you get these sort of quite worrying curves, I think, where for 24 runs at 3T, that's 8 minutes per run, you have an explained variance which is acceptable, like I think it's 36 or so. And to achieve the same point on the 7T in the same subject, you need only 5 runs. That's one subject, but we have another one here which actually needs 8 times as many runs on the 3T as it does on the 7T. Now, even if you have to pay extra for scan time on the 7, I don't think that this is a difference that you can ever work across. People will not stay still. They will not come back 6 times just to do your experiment. So there's, it just might carry across, give you the power to actually do the experiments. Okay. So the other point I mentioned was the echo time. The Bolt contrast, it's a T2 star dependent contrast, so we're looking at something that changes with echo time. If we look at the T2 star map, well, you can't see the numbers on this, but the average T2 star at 70 in the gray matter is about 30, 25 to 30. So if we look at a signal decay curve from 0 to 50 milliseconds, then round about, so it's a decay of about 25 milliseconds. And if we increase that by having activation, we have an increase in T2 star to 27 milliseconds in this case. We get a curve that the difference is broad. It's a broad bump, but it's very much at its maximum between, 20 and 30 milliseconds, probably 25 to 30-ish. And that limits how long your readout can be, because if the center of your readout, the crossing of the center K-space, has to be at this point, then you cannot have a readout of 200 milliseconds, even though you might like to, because then you can acquire nice lots of points and have low acceleration factors. So I think this is actually a slide John's nodding, but I think this is a slide that John already also has in his presentation. But it's a very important one. So if we're looking at laminar imaging, we're studying the cortex, and the cortex is not a homogeneous thing. It's actually a very funny structure in that the blood's coming out from the outside, coming in from the outside, and it's also draining upwards. So all of these veins, they all go in the same direction. It's one big pooling towards the cortical surface, especially in T2 star weighted data. So we see that across the laminar literature, we have again and again these same graphs which go from normalized cortical depths of 1 to 0. They always go up, sometimes in a straight line, sometimes there's a bump, but they always go up. What's also interesting is that you can see the pooling in that the responses are a bit later as you go towards the cortical surface. So what you have to remember from this slide, right, is that it's important to properly draw where your cortical lamina actually are. And for that, we need a really good anatomical image. No matter how you do it, you have to start with a good anatomical image. So typically, people use T1 contrast because then you have a nice spread between the grey matter, white matter, and CSF. And most of the T1 weighted anatomy at 7T is acquired using MP-RAGE or an MP2 RAGE or something like it. So I thought I'd show you the sequence here quickly. So we have, in a standard MP-RAGE, you have an inversion pulse, wobbly thing on the left, followed by a readout. So where the center of that readout is the center K space is what gives you your T1 contrast. Then you get images like these. This is actually, I like to think, a decent example, but what you can see from this is that there's a massive bias field over this image. There's what you see by eye, you have good white matter contrast, but it's not homogeneous enough throughout that you can automatically segment it. If you give this to SPM, let's say, then it'll mess up, especially in the temporal lobes. So, which is why people usually take a little step extra to acquire their anatomical data by, for example, acquiring a self-bias field corrected MP2 RAGE, where we have 2 of these readout blocks after the inversion pulse. The first one has all the contrasts that the MP-RAGE also has. The second one has everything but the T1 weighting. So that would look something like this, but this is a very heavily T1 weighted image on the top left. And you can see from the phase that there's still, the white matter still has to go through the null point. So there's a 180 degree phase difference between the grey and the white. If you combine these, then you get an image which is relatively free from T2 star, from at least the received B1, and from the M0 distribution. So then we have an image which we can actually automatically segment nicely. You can also acquire a T1 map from that if you like, calculate a T1 map. Now, if this is everything we would like to do, well then why is it so hard? So I thought I'd put in a slide on the limitations of these. So first, we're limited by how good a magnet we have. We're limited by mostly by how strong the magnet is that happens to be in the place where we work. Right. We're also limited by how good an RF coil we have. And like I showed with the PubMed graph, you can buy coils, you can make your own coils. This is a lot easier than changing the field strength that you work at. But you have to make sure that your particular coil is tuned to the field strength that you're working at. So if you're buying a very, very fancy new exciting scanner, then it may be very difficult to get appropriate RF coils. And the coils that are available for 3T might be more mature than the ones for 7, for example. What we also need is a very good field inhomogeneity, because of the sensitivity of the EPI readout to field inhomogeneities. And shimming is a lot more difficult as you go up in field strength. We need super good gradients. And unfortunately, if we get super good gradients, sometimes the RF coils don't fit inside them anymore. They may also interfere in very nasty ways with your main magnetic field. So given this nice little knotted version of limitations, it's now time for my next question, the third one. So what do you think, and now there's enough people to have some stats on this, is actually the best field strength to do laminar imaging at? Okay. And now, did you have your phones out? Prepare a question also, if you could. So, physiology, right. So even if we'd have the perfect system with a super magnet and super gradients, there are still limits that we really have to stay within dealing with physiology. So you cannot simply expose a human volunteer to any field strength you like, or better, you can't expose them to a change in field strength that you like. If you push someone very quickly into 70, they will be dizzy. If you push them into 14T, I don't want to know what that feels like. What you also have to take into account is simply how much noise your imaging causes and what that might do to the hearing of your subject. If you really push your system, there's a limit how fast you can go. Same for the peripheral nerve stimulation. Most subjects are okay with a little twitch here or there. It's less nice to withstand hours of pain. And of course, the SAR, so the deposition of RF, and the heating that might cause in the body is also, there's a hard limit on this. You cannot heat more than what's caused by this 3.2 watts per kilogram. We're stuck with that. So even if you think of a super clever acquisition scheme, these are things that you have to stay away from. And then I'll just put it here again as a primer for the rest of this session. You also have to think about what happens with your bolt sensitivity to draining veins in a profile over the cortex. So in summary, we've looked at SNR and where does the signal come from in MR and how can we increase that. We've looked at K-space and how to sample in such a way that you get high spatial resolution. We've also looked at the bolt responses and the influence of the field strength on that. I've shown you some of the anatomical images that we've acquired, and then I talked briefly about limitations of the thing. So then rests me nothing but saying thanks to you again for showing up so early on a Sunday, and to my collaborators for lending me slides.